Welcome to Miner's Tube. Today we're diving into the world of cryptography and blockchain, with a deep look at Zama, a cutting-edge open-source project that uses fully homomorphic encryption to bring confidentiality to smart contracts and on-chain data. Whether you're a developer, crypto enthusiast, or just curious, stick around. First, let's briefly understand fully homomorphic encryption, or FHE. Traditional encryption lets you encrypt data, but if you want to compute on that data, e.g., add, multiply, compare, you must decrypt it first, exposing it. FHE is a special cryptographic technique that allows computation directly on encrypted data, meaning you can perform operations without ever decrypting. In other words, it keeps data encrypted at rest and in motion, even during processing. The result is another encrypted output. Only the authorized party can decrypt to see the result. Because of this, FHE is often called a holy grail of cryptography. It offers privacy and confidentiality while preserving utility. However, FHE is computationally expensive and technically challenging. Historically, it's been too slow or resource-hungry for many practical applications. That's where Zama comes in, aiming to make FHE practical, scalable, and usable on blockchains. So what is Zama? Zama is an open-source cryptography protocol project focused on bringing confidentiality to blockchain and DeFi via FHE. From the Zama homepage. Their vision: enable confidential smart contracts by keeping on-chain data encrypted end-to-end, even during computation. Zama. In other words, Zama is tackling a core limitation. In blockchains, all data processed by nodes or validators is typically visible. Zama wants to change that. They propose to layer Zama confidential blockchain protocol on top of existing base chains, L1 or L2, so developers can build confidential applications without giving up decentralization or verifiability. Zama. Their architecture uses what they call co-processors to offload FHE computation, thereby keeping gas costs lower and enabling horizontal scalability. Zama. They also emphasize ease of developer experience, using solidity and marking data types, e.g. uint, to specify which parts are encrypted. Zama. So Zama is effectively bridging the gap between cryptographic theory, FHE, and real-world, scalable blockchain applications. Let's break down the core components and how Zama works in practice. Encrypted data types in smart contracts. Zama introduces encrypted data types, e.g., uint, ebool, that you can use in Solidity code. Developers mark which variables should stay encrypted, and those operations are done under the hood using FHE primitives. Zama, for example, you might have an encrypted ERC20 contract, where token balances, transfers, etc. all remain encrypted, and comparisons or arithmetic happen using FHE functions. Zama coprocessors, FHE offloading. Because FHE is expensive, Zama uses coprocessors, external compute units, to handle the heavy lifting of FHE operations. Zama. This keeps the base chain, L1 or L2, from being overburdened, helps manage gas cost, and allows for better scalability. Public verifiability, plus confidentiality. A key promise: although data remains encrypted, the system should still allow for public verifiability, i.e., anyone can verify that the computation was done correctly, without seeing the private data. Zama claims to offer compliance-friendly confidentiality. You can encode rules for who can decrypt which parts of data, based on conditions coded into the smart contract. Zama performance and throughput. Zama states it is already faster than Ethereum in terms of throughput, 20 transactions per second per chain, with plans to scale further. Zama. They also plan to use FHE ASICs, specialized hardware, to push this to 10,000 plus TPS in the future. Zama. Their roadmap includes improving scalability and performance, and making the protocol production-ready. Mainnet is projected. Zama use cases. Zama enables confidential DeFi, token swaps, lending, yield farming, etc., without exposing amounts. Encrypted payments, stablecoin transactions where amounts remain hidden. Private token launches, airdrops, governance, transactions and rules encrypted, but still verifiable. Sealed bid auctions, bidding information hidden until reveal phase, preventing front-running. RWA tokenization with compliance, real-world assets tokenized while preserving confidentiality and regulatory constraints. On-chain self-custodial banking. Users' balances and flows remain private on-chain. All these are spelled out in Zama's ecosystem descriptions. Zama. Of course, Zama is ambitious, and there are challenges and trade-offs to consider. Performance overhead. FHE operations are computationally heavy. Even with coprocessors, latency and cost may remain non-trivial. Hardware dependency. Achieving high throughput may depend on specialized hardware, ASICs. Complexity. Developers will need to adapt to new patterns, encrypted variables, decryption permissions, which raises learning curve. Trusted setup or assumptions. Some FHE schemes require underlying cryptographic assumptions. Any weaknesses could impact security. Ecosystem maturity, adoption, tooling, auditability, interoperability will all need to be proven in real-world settings. Regulatory and compliance constraints. Designing confidentiality that also meets legal disclosure, auditing, and compliance requirements is tricky. Nonetheless, Zama is making progress, with public testnets already live and plans for mainnet in Q4, per their roadmap. Zama. Why does Zama matter, especially now? One big problem with blockchains is that transparency is both a feature and a bug. All transaction data is visible to anyone. Zama challenges that. Zama privacy is a growing concern. Financial data, voting, identity, commercial secrets. Many applications cannot tolerate full transparency. Zama offers a path to selective disclosure, allowing privacy while preserving verifiability and decentralization. In DeFi, the ability to compute privately, e.g. run credit checks, risk analysis, reward distributions, without leaking data is a game changer. If successful, Zama could unlock new use cases in regulated finance, institutional adoption, confidential exchanges, etc. Also, Zama is part of a broader movement, combining cryptography, zero-knowledge proofs, MPC, TEEs. But FHE offers a more seamless, composable approach when it works well. So what's next for Zama, and how can you get involved? Zama's public testnet is already live, and they aim to launch mainnet in Q4. Zama. They are building developer tooling, docs, and community resources to onboard smart contract and cryptography developers. You can check out their GitHub, developer docs, and research papers, linked from their site. Zama. If you're a developer or cryptographer, you can experiment with their encrypted types, sample contracts, or join their developer program. Keep an eye on hardware advances. FHE ASICs or coprocessor architectures will be critical for scaling. In closing, Zama is pushing the boundary of what's possible in private, decentralized systems. It's an exciting fusion of cryptography, blockchain, and privacy engineering. Thank you for watching. If you liked this video, hit like, subscribe for more crypto tech content, and let me know in the comments what you'd like me to cover next. Maybe a deep dive into FHE schemes or how Zama compares with other privacy protocols.